Let's go through LEED code 1122. Lowest common ancestor of deepest leaves. For this question, it gives us a binary tree, and it asks us to find the lowest common ancestor of deepest leaves. So it has a definition of the lowest common ancestor. That is it is a set of the ancestor is that for every node, right? And we will have the node A will be the largest depth, such that every node in S is a subtree of root A. So we want to find the root A. That means for this kind of, if we read this kind of sentence carefully, is that, for example, we find our deepest node, right? And that is 7. And this is also one of the deepest one. And we'll see every, for example, we have another one, which will be 9, right? So we'll see this one and this one has a length 3, and this one has a length 3. We need to have every deepest node leaves will have this kind of will find a node. The subtree will be will include those leaves. So let's say for this kind of scenario, we change this a little bit. It will be 3, and if we don't have this 9 node, right, it will be 2. And also, the question says that for the example 2, if the tree has only one node, 1, then it will be itself. And the example 3 is 0, 1, 3, none, and 2, right? So let's say that this node is the deepest one, and so it will also be itself. So for this question, intuitively, we can think about divide and conquer. That is because we need to have the lowest common ancestor to include all of the deepest leaves. So if we'll say we can find something like find the depth. If the left child the depth equals the right child depth, that means we have a deepest leaf on the right tree. We also have a deepest leaf on the left tree. So we can only have return the root, so that it will include all of the subleaves, right? And if we write those function, if the on the left the deepest leaf length is greater than the right, then we just try to write the same function, go to the left, recursively call the left child to have the return the left LCA deepest for root to the left. The same thing with if this one, the right root has the deepest length greater than left, we call this on the right tree. So let's write the recursive function quickly. If root equals none, we just return root. We're going to have a function called get depth, get max depth. return some kind of int, right? So we'll say if it max, let's put this int L max equals it max x root to the left int right max equals it max depth root right. Let's say if L max equals right max, we just return root. Else, let's say if L max greater than right max, so the deepest common ancestor can only be on the left child. So we'll just return LCA deepest leaves root to the left. The third scenario is return LCA deepest leaves root to the right. We write this help function get the max steps. Let's say if node equals no, return 0. Otherwise, we just return max dot max. It that's root dot node to the left. It maps node right, and we are +1, right? It max depth dp dep th 38 get max depth. So let's say this is pretty fast, and we have two recursive call. This one also use a recursive call to call this function itself. But when we analyze this kind of message to do this question, we find even this is fast, but the time complexity may not be that good. Let's go through this tree, right? We need to calculate the left length, deepest length, right here, and also the right deepest length. So we'll find that the left deepest length is greater than the right. Then we go to this tree, and when we go to this tree, what we're going to do is that we'll go to this child, and this child again to calculate the length. We call L epsilon, right epsilon. We'll calculate this number and this number again, right? Actually, when we calculate this L, it's already calculated this. So we have multiple calculations. So this method, it has time complexity because we'll say the root, it is this one, is calculated 0 times. This is calculated 1 time, right? For this node, this layer will be 2 times. And so we all say it depend on the length of the tree. So it will have this one calculated once, twice, three times. It will be 1 plus 2 plus 3 plus until the depth, right? So this one is around in square time complexity because we have multiple calculations. So if we want to save have better time complexity, we should find some way which we, for example, this L epsilon we already calculated, and this right epsilon we already calculate. If we can use some kind of way to record those number, then we iterate to this node again. We don't calculate it again. So what we think about is this is like a DFS, right? And we can write a memo to record the node. If this node we already calculate, we just check whether we our memo have this value calculate or not. So let's change this code a little bit. So what we need is that we can add a hash map, right? And the key will be the tree node, and the value will be the deepest length. We call memo new hash. And we can have a hash map tree node integer memo. Let's say if memo contains key this node, right? We just return memo get node, and we have int result equals memo put this node result return result, and new hash map. Let's put this one here, and we added the memo here. Yeah, we should have this one. You see, use this way, we for every node, we calculate just once. So the time complexity it is improved. For every node, we just calculate once, so it will be O(n) time complexity. But when we see the result, the submission result, it's not that good. It become 5 milliseconds and only beats 11%. And originally we didn't add a memo. It is 1 millisecond. The reason is that this is a this kind of data set is very small. It's less than 1,000, less equal to 1,000. And we have a hash map, and hash map, we hash a tree, and it will also add internally, it will hash a very complicated object. So it get our it improves the time complexity, but for this small data set, it will even be slower. We notice this kind of tree say that the value of the node tree are unique. Possibly we can change this one to be integer, right? And we put a to integer. So if this one contains node dot value, let value. I think in this case, we just need to hash an integer instead of hash the whole tree. This way, we can improve our result. Improve the tree node cannot int cannot. Sorry, we don't need to change here. Now it improve a little bit, goes to 4 milliseconds, and but still not that much. We'll see the number is in this range. Another way, let's try to see. We can just use an integer array. Memo equals to new 8. And by default, it is yes, it is the value is from 1 to 1000. If if we are say, let's say if this one int value equals no, not value. If this one does not equal to 0, return memo value memo int memo value equals result. Yeah. So we'll say we add a memo. The actual for this question, the time is still longer than what we do originally. We didn't add a memo, but the thing is that if the data, for example, the data, because the reason is that the data is just 1000, and it is a very small data set. But if the data goes very big, this kind of time complexity will be n time complexity, right? And now we have a so this will be better than our first approach. And also space complexity, we have recursion, right? So every node we need to iterate once, that is also ON.